Good morning, everybody. Welcome to this chapter 9. We'll be starting this chapter 9 on subroutine and control abstraction. Subroutines and the control abstraction. First, let's talk about functional abstraction. A function is a way to modularize a certain set of the function call. And a function performs a specific task given stated preconditions and the postconditions. So basically, a function is certain call that you assign a certain mission that you want to accomplish. And in doing that, you will need some preconditions and some postconditions. The preconditions and postconditions are different from the prologue and the epilog. Preconditions are the requirement that need to be met before entering into this function. For example, we have a function called reverse of a string. Then the precondition should be the string need to be non-empty. That can be one of the preconditions. Of course, certain reverse function for the string doesn't require that, but let's assume that this specific reverse function has such a precondition. And the postcondition is this output string that is reversed. And that reversed string in Java will be a separate string from the original string. Then this will be the postcondition. So precondition and the postconditions are what we need to meet before we can perform such a function, or what we can expect from the output of the function. And by doing this, we actually form some abstraction of a certain module of the code. We call it function. So basically, we can treat the function as a black box. This black box actually try to accomplish a certain goal for us. And then we assign such a goal for that function, and we would like to have that function to perform for us. So that is called functional abstraction. And for abstractions, we not only have this functional abstraction, we also have data abstraction, and we also have the function and data abstraction. People call it information hiding. There are several levels of abstractions. So in this chapter, we will be focused on the functional abstraction, and chapter 10, we will be on the object-oriented programming, which will be on the information hiding. That is more than data abstraction. It is actually data and the member functions abstraction. It's whole object level abstraction. And we can also use the module to provide some sort of abstraction. So module namespace, it is another way to do abstraction, and they are higher level compared to this functional abstraction. So for a function, it has a name, parameter, and the return value. And we can call it as the input, that's the parameter, and output for the return value, and its name, that's the functional name. It may be used by name as long as appropriate value or object is passed to it as parameter. So the preconditions are met, and you pass the right parameter in. And the postcondition, as long as its return value is used in an appropriate context, that is the postcondition. In this sense, we have abstracted the function and hidden its implementation details. So basically, you provide the parameter list and a return value, and set up certain preconditions and the postconditions. And this, we can abstract the function. But this precondition and postcondition are different from the prologue and epilog. The prologue and epilog are used to set up the function call in lower level, such as the assembly level, and it is different from this precondition and postcondition. Precondition and postcondition are used to describe the requirement of the function so that we can achieve the goal that we assign to it. A set of rules For a certain function that we describe here, or we call it subroutine, here are several different things that are similar to subroutine. It includes a code section, subroutines, procedure, operation, function, and method, and lambda expression. For code section, for code section, actually sometimes it's just a cobra, and it doesn't have any name or parameter. So this is some sort of a abstraction, but it doesn't actually hide the implementation detail from the user or the programmer. Subroutine sometimes refer to some function that has no return value, but it is not always the case. So subroutine is a more general term, and it can sometimes represent all of the rest of these. Procedure usually in some language like Pascal, it is used for some function or subroutine that has no return value. Operation, we are talking about some operator like plus sign, minus sign, concatenation, shift left, shift right. Itself can be considered as a function, but it is not in the functions format or subroutines format. And function, we know in mathematical meaning, you provide input and it will generate an output for you. And method usually is some sort of specialized function for a certain class or object. And the last one, lambda expression, it is also some kind of a function, but usually it is anonymous, and it can be used as an anonymous inner function that being used for certain code, that being used in part of the inner part of a certain program. So these are different ways of setting up the subroutine, and they have different definition and different application as well. The advantage of functional abstraction, including modularization, code reuse, packaging, teamwork, abstraction, and readability. First, for modularization, we decomposing a complex problem or a complex programming task into simpler steps. So basically, we break down a big chunk of a code into smaller pieces, and this is called the modularization. By doing this modularization, we actually need to assign a certain name and parameter and the return value or some namespace. So it provides a certain way of abstraction. So with that name, you don't need to know about the detail in that function. So the modularization actually provides some sort of abstraction and not hide implementation details. And because of that, we can actually, with the modularization or packaging, actually we can enable reuse of code across multiple programs or even multiple platforms if all of the different machines sharing the same virtual machine of different implementation. So that actually is one way to do packaging. For example, in Java's case, a package can be done in bytecode, and the bytecode can run on different virtual machines. So it actually is a way to reuse the code across multiple programs or even multiple platforms. And that actually enhances the code reuse to reduce duplication of code within a program or even within different programs. And that actually also improves the readability, improving the traceability, because we always know that a certain function has certain name instead of reading a big chunk of code. And by modularization, you can also assign the programming task among various programmers or various stages of project. You can assign to different people, so it can enhance the teamwork as well. So these are the advantages for modularization or functional abstraction. For a function, we usually will see something like this. We have a header and we have a call definition or implementation. The header part, sometimes it includes the visibility, the scope, the generic variable, and the method signature. The method signature sometimes include the name of the function or method and a parameter list. And so this is a complete description of a header. And for some language, this header put into a header file like C language, so that it can use it for cross reference. So two functions can actually, with proper header, can call each other without the problem of the order of the definition of the function. So this header is very important for some language like C, C++. And anything below it within the braces is called the body or the definition of the function. So these are, and also you can call it as implementation of the function. So these are the two main parts for the function. And generic actually create the type variable or type parameter that you can pass it with type argument that would make this function to have multiple use for different data type. And scope will define where this program will be stored and how it will be executed. And visibility define the possible usage of this function, whether it will be open to public or it will be only a private function within certain class. So in this chapter, we will be touching these different topics: call stacks, calling sequence, parameter passing, exception handling, and call routines. And in this session 1, we will be focused on call stack, calling sequence, and the parameter passing. And call stack actually talking about the data structure that is going to support the function or the calling of the function. And calling sequence actually talking about the operation that a operation system or a compiler or a runner will actually facilitate the function call. And parameter actually talking about the transition of the data. And these are the topics for this session 1. And session 2, we will be talking about exceptional handling. That is a special type of functional call. And call routines are recursive call that for functions or subroutines that can call each other. So these are the topics for this chapter, and we will be focusing on topic 1, 2, 3. Stack layout. Stack layout will talk about the call stack and the data structure that will support the functional call. Let me go back and check if anybody show up today. Okay, I'm alone, but it's okay. I'll continue. Now we will start to talk about the data structure that will support the function call. And first thing we would like to talk about is the static functions or methods. For static functional methods, actually we are talking about the call and for each function, for each method. And usually your method or functions, no matter it's static or it is a class member method or a function, it is stored in a static area. So the call is, no matter it is static or non-static, it will be stored in the static area. And global variable will also be stored there. And the class only variable, some class only variable will also be stored in the static area. So this global variable and the class variable actually are of different concept, but they may or may not exist in one language, but if they exist in certain language, it will be in certain static and not dynamic memory. So we will be discussing this static memory and dynamic memory later, but basically these are something to be stored in the static area, and it's implicit constant, including strings, or sometimes we call it interned string, interned string. That are some constant or literal string, like you use the double quote and to enclose it, something like a double quote, I love Java, something like that. Those strings are actually called intern string. That will be stored in the static area, and set and other aggregates. Small scalars may be stored in the instructions themselves. This depends on the compiler. Usually, it's possible that you don't want to actually run it, actually load it from memory, and you just generate some constant. For example, like 5, you put into the instructions data field instead of fetching it from certain memory. So that depends on the compiler as well. Method area, or what we call the static area. As we mentioned, right here we have a method table. And the method table actually stores all the methods, including the static method and the instant method. And this table will also point to a certain implementation area for the methods. So actually, sometimes you can think about this Java's method area method table like the virtual functions V table or V vectors, V pointers. So that is the method table. And we also have the method information that actually usually is just recording the different information that need to support the method call. And we have the type information for different type defined in that class. And also you may have the constant that will be stored here. That is the intern string and those different constants. And field information and the reference to class loader and the classes. So some classes that is required for this class will be put in here. Class variable will be the static variables. So this is the Java way of implementing the static area. And these are related to the static method or class methods. Right here, we talk about the dynamic memory. Java has the dynamic memory of the stack and heap memory allocation. So heap is used for those reference data types object. I mean the object, not the reference itself. So basically, you have a reference that you created in certain function or method call, and that actually will create a object in the heap, and the reference will be passed back to the call stack or the global static area, depending on where the reference is. So that's the heap. And call stack actually will be storing the call frame, and we explained it already regarding the call frames. And actually, these are the call frames that will be the. So stack and heap are considered to be dynamic because stack you will have push and pop function. Heap actually you will have the create and the free function, memory allocate and free function. So both of these are considered as dynamic memory. They will exist at runtime, not always there. And the previous method area will be existing when you load the function. And object reference is a pointer to handle pools, and the handle pool including pointer to object pool that actually will point into the instant data, that is object pool that is in the heap. And some pointer will actually also point into class data. For example, the intern string And if you have some pointer to like class data, it will point into the method area that is static, and heap is dynamic. And this handling area actually can be inside your object, and actually, and some object may have data field, and that data field can point into the instant data or to the static data, and that reference may be stored in an object reference, and that object reference can be in stack or sometimes in the method area as well. So actually, you have to know about whether the reference is right now is dynamic in stack or it is stored in a static area. That actually depends on how you define it. Right here, we have a class method area in stack dynamic. Let me explain from the from the right to the left. And these are 3 different levels of the code. And let's start it with the Java code. Java has a frame. We call it Java frame. And the Java frame may call some native frame because there are some implementation or used for the Java virtual machine. And when you call a Java function call, say we create a thread or something, and those threads actually need to call C language native code on certain machine in order to make it happen. So in the code stack itself, actually you have your Java frame and native frame. And in the execution, you have transition in between. You have some call frame, you have Java frame, and you have the Java to native area, and you have the native frame. So actually in between the code stack, you have something that is shared or temporary that is shared between Java and native frame. And this is higher level view for Java code stack. And actually this, if we translate it into C level, it will be looking something like this. This is called C code stack. And in fact, this every Java frame can be written in some sort of C language like format. And actually, these are different frame that can be implemented in C level. And in C level, actually, we have certain parameter, return address, and local variables for a certain function, and we call this as a stack frame or call frame for a certain function. So anything in this Java frame can be actually implemented or conceptually be transformed to something like this. But this is not really something happen on the machine. And this will go down another level, and in compiler from C level, it will be translated into a assembly code, and the real things that store on the memory or the code stack will be something like this. So Java compile to some bytecode, and the bytecode would be similar to something like the C level code, or sometimes is similar to assembly level code. But anyway, there is another layer of the translation from that bytecode to assembly code, or from C code to assembly code. And then eventually we will have the assembly level code stack. And right here, as you can see, we have local storage that is for this local. We have parameter area that is for this parameter area. But there are something not being shown. We call it an implicit actually code frame, part of the code frame. We have the return address and the frame pointer being stored in here. And actually it is shown only for the return address when you look at it from higher level conceptual idea. And actually you need to save the register and save the link register that actually link to the code frame of its parents, something like that. That need to, the link register need to be recorded as well. And you also have the set frame pointer for the previous code frame. And you need to set up the new stack pointer and the new frame pointer. And The parameter part, we call it the caller area, and this set register, set link register, set frame pointer, and set register, and the local storage, we call it the callee part or callee safe area. So basically, something that you pass as parameter, we call it as the caller area, and this caller area usually is shared by caller and callee. Both of them can see it. So actually, this caller area and the callee area, the parameter actually is right here, something you shared. And the local variable is not shared, actually is callee only, and you have the link register for global variable and the set register for the previous coframe, and these are in the callee area. So local storage actually will be happening on any definition in the code block. So this is how conceptually we translate from higher level code to lower level code, and this can be the C code stack or the virtual machine bytecode level. We will show you some example later. And from this level, you again translate to the assembly level. And the real coframe is on this assembly level. And right here, we had a review for stack layout allocation strategy. One thing I need to point out is that this chart is not 100% exactly right. So you have to use your imagination. And actually, this figure is taken from figure 3.5. We already seen this already when we explain the static scoping and the dynamic scoping. Let's start it from here. Given the calling sequence A called E and B, A function or A subroutine will call E and B, and E and B as called, so we call A first and then E and then B, and then D and C, and then D and C are called. So we call A function first, and then we call B, and then we call B. I'm sorry, we call A first, and then we call E, and then we call B, and then we call D, and then we call C. But remember, this is the order of the coframe. So this actually is the order of the coframe. This is not what will be happening on the stack. So be careful for this 9.1 figure. And the frame will be allocated on the stack as shown on the right with the indicated static and the dynamic links. So here I have to be precaution you. So A calls E, so E is here, and suppose E finish, and then we call B. But it's somehow shown like E calling B, but that's not true, okay? And there's some reason why the author draw like this. Now, let's explain it. Within A and E routines, within A and E routine, we can see A, B, E are all visible, because all of them are defined in the subroutine A area. And C and D are not. But within B, C, D, we can see all of the A, B, C, D, E with the proper static link. So let me explain this static link. Static link is for the static scope. So A call B and E and B. So B and E need to have a static link to A. So if some variable that is defined in A function and B and E or B or E reference it, it had to go back to the coframe for A. And C and D that is actually called by B function. So if there is a variable that defined in B function and not in C and D function, and they need to have a static link go back to B level. But it's actually happening on C language, but not in Java language. Well, Java won't allow something like this. And let's go back to the slides. Those are the same link register that will be pointing to the parents. And on the right hand side, actually, it's establishing the static scoping. So something that you need to go back to your parent to find the definition is static scoping. And right here, it's called dynamic link. So this side is used for dynamic scoping. So this figure actually showing both static scoping and dynamic scoping. And for dynamic scoping, the reference environment is the one closer to you. So A calls E, so E need to go back to the caller to find its binding reference environment when you use the dynamic scoping. So here in this chart, you show both the static scoping and dynamic scoping in one chart, but this won't happen in the real language. Now let's further look into the stacks. The code stacks will include the parameters, local variables, temporaries, and the bookkeeping informations. And the bookkeeping information, we may show this later, but right here, you need to know about parameter, locals, and temporaries. Temporaries are some right-hand side value that actually you generate during the execution of the function, but you may not be able to see it from your language level, high-level language level. And heap is used for dynamic allocation that we experimented already. And for bookkeeping part, including the return address or return program counter, this is actually dynamic linking. And save register for all the register R1 to R16 or R15, something like that. You actually need to save the current process status before you jump into a function. And the line number that you actually will call to. And then save the display entries and static links. So these are called the bookkeeping part. And this bookkeeping part is right here, this middle part that I call it not visible to the programmer part. These are the so-called bookkeeping informations. So the bookkeeping informations including this. And then argument and return and local variables. These are not bookkeepings. These and the temporary variables that are shared between the arguments and of the caller and callee. And these are the basic content for a code frame. Now let's look at the calling sequence. Calling sequence is different from the call stack. Call stack is about the data structure that will support the functional call. And calling sequence actually is the control for the calling sequence, for the functional call. So for calling sequence, it is used to maintain a stack. Calling sequence actually is to maintain the stack or calling stack. It is the responsibility of the calling sequence or subroutine, prologue, that's call, or epilog, that's return. So actually this is the pre-procedure for calling the function and the post-procedure for calling the function. So actually this is something done before the function call and something done after the function call. So space is saved. We put in as much as possible in the prologue or epilog as possible. So if we done more on the subroutine, pre-processing part or post-processing part, actually we can save the code frame, make the code frame to be smaller. And time may be saved by putting stuff in the caller instead of the callee. Because if we put another thing in the callee side, actually when you need to do the context switch, you call the call frame, you need to access a lot of memory that will waste time, where more information may be known. For example, there might be fewer registers in use at the point of call then are used somewhere in the callee. So try to minimize the callee will save time, and try to push the prologue and epilogue to be bigger will save space. And here are the tasks to be done for prologue and the epilogue. So for prologue, you need to pass the parameter. So put those parameters into your call frame, and then save your return address and change the program counters that actually jump to the function code. So let's return to the procedure. So in the procedure, first we need to save the parameter. It's right here. And then we save the program counter that actually is someone who will call this function. And then we will actually jump to the function's call reference address for the call body that define this call body. We jump to there. And then if we have the definition for local variable, then we push those local variable in. So when we call a program, first we pass the parameter, save the return address that is someone calling you, and change the program counter. We change a new program counter, and then we change the stack pointer that actually advance the new call frame, and then we save the register from the CPU into the call frame, and then we change the frame pointer to refer to the new call frame, and then we execute the initialization call for the new object that is local variable. So these are the procedure for the calling part. For the return part, we return the return parameter or functional value. So we actually pass the return functional value into the higher level or the caller part, and then we execute the finalization of call for the local variable. So basically, if there are some object, we need to free all of them, something like that. This is executing the finalization call for the local object. Deallocate the frame called stack frame. So we destroy the frame, and then restoring the stored and restoring other stored register from the call frame, and then restoring the program counter. These are the things that we need to be done when we are returning from a certain function. So right here, we have a structure of a procedure, and alpha is the caller, beta is the callee. But remember, this chart is the calling sequence in time domain. That is not spatial domain. So this chart, the structure of procedure is different from this call stack. So don't get confused by the call stack and that procedure structure of procedure. Call stack is the memory storage, and this one is scoping chart, and this one is structure of a procedure. These three are totally different. So let's look at this. First, we save the register, retrieve the parameters, and then save, unsave the registers, send in the parameter when we start to call a certain function. So if you look at this from here to here, actually, it is doing something that you are doing for Prologue. Then we call procedure, we change the program counter, and then we go to the beta, the callee. And in the callee, we save the registers into, we save the callee's register, the caller's register into here. And also we need to save the link register to its parents. So save the unsaved registers, send in the parameter, put it into the call frame, and then call procedure if you have subroutines to call, something like that. And after you execute the program, you from the subroutine you receive the result, and then you restore the unsaved register, and then we return the result actually from the And this one actually received the result from the subroutine for beta, maybe gamma or something. And then you restore the unsafe register from gamma. And then here is the finish. Here the green and this part, green, blue, and this brown part actually is the epilogue for this beta. So this beta actually, you will return the result to here, restoring the same register to return to this here, and then return. You jump back to the procedure that call is callee, and we finish the whole calling sequence with the prologue and epilogue for beta. And for alpha, it has its own prologue and also for its epilogue. And remember, this calling sequence is time domain, not spatial domain. So the calling sequence, you can see from what we talk about for prologue and epilogue, and the structure of the procedure, it already show you very clear. So the ideal approach is to save those registers that are both live in the caller and needed for other purpose in the callee. So we try to make sure caller and callee has the right data to operate on. How to determine this intersecting set? So the common area, the temporary or shared call, is very difficult to determine. Common strategy is to divide the register into caller saved and the callee saved set, and if possible, of equal size would be better. Caller uses the callee saved register first, and the caller saved the register later if necessary. And local variable and argument are assigned with fixed offset. This means the local variable that you call in here or in here, you have the fixed offset from the frame pointer. So your local variable have fixed edges offset from the frame pointer. So you can actually see the frame pointer, and then with some offset, you can get some local variable. And step pointer actually is for pushing and popping purpose, to add another layer of the function code. So it's different. Frame pointer is used to address to the local variables. So here actually is more like a frame pointer at compile time. And while stack pointer may be okay, but I don't think stack pointer is not appropriate. Some storage layout use a separate argument pointer, and this is possible. And the VAX architecture encouraged this, and actually this is not important. VAX computer already managed. And here are the convenient name for the registers. So we have these are the basic important bookkeeping registers that you need to save for return address, procedural arguments. You actually can put these into certain registers, so your operation will be faster instead of going to the memory for memory access. So let's look at this. At assembly level, you may store everything in your main memory with the code step. But in modern RISC machine design, you can just put those procedural codes in a register. Since the on-chip register file are much bigger now, so you can actually use this argument 0, argument 1, argument 2, argument 3. Remember that when we have the YAC, we have the YAC for parser. It uses a lot of this $sign for the parameters. So remember, these are of the similar purpose. you actually use this name to denote for certain registers. And this is the basic bookkeeping part. And you may have the caller safe part and putting into the caller safe area, including temporaries, and maybe overwritten by code, procedure, or colleague. So the temporary part, we use the T for the name. And the caller safe part, we put, colleague set part, we actually write as S. And this part is actually by caller, this part for colleague. And colleague may have another set of the temporary area stack pointer return edges right here for caller safe. So these are the different names in the register level, and this will help to minimize the access for the main memory. And what's that used for? Basically, on the RISC machine, we have one A call frame for procedure A, and actually procedure A will have some value that actually will be the parameter for B procedure. So A's output will be the input for procedure B. So they have some overlap. These are the parameter area. So when we do the process, we have process 1 as red and process 2 are blue, and we have R3 and R4 that are shared by these two processes. So one call frame is put into the RISC machine as a register section, and another process occupies another register section, and we can actually use the register as the call frame, so we don't need to access the memory so often. That is the register file, and register file can be treated as a circular buffer, and this circular buffer actually will rotate. If you keep calling and return, you will come back, something like that. So you call, return, something like this. So if the circular register is out of space, then we just dump part of the register file into the memory. But if not, you try to make a circle. That will make things faster because you have this operation to be call, and then return, go back. So call on one direction, return on the other direction. So conceptually, if we look at the register file, it would have the caller's name like this, and the colleague's name like this, and there are certain variables being shared together. And the assembly code would be something like this. So typical calling sequence, and we are talking about the epilog and the prologue again. And the real memory address from the textbook is something like this. For the code stack, it will be something like this. You basically, for caller, you put the argument. So caller's information usually is the argument. And then you start to put the caller's address, return address, that is usually the next statement after the functional call. You store here, and if you save the previous frame pointer for the caller's frame pointer, save the register for stated link, the reference to the previous level or the global variable, and then you go back to the local variable that is for this current frame. And temporary means you create certain object that has the pointer pointing to the heap, something like that, and then you prepare a argument list for the next call frame. And stack pointer keep moving up if they are something added to this call frame. So this pretty much is brand whatever it writing down over here. So you can actually study this by yourself. That's what I described over here. Now we have a calling sequence in this low-level virtual machine on ARM. What it is, ARM is a processor, and you can have a low-level virtual machine low-level virtual machine is written in C++ and is designed for compile time, link time, runtime, and the idle time optimization of program written in a certain arbitrary programming language, originally implemented for C and C++. The language is agnostic design for low-level virtual machine has since spawned a wide variety of front-end language with compiler that use LLMV, including these all use the LLMV. So it's some sort of the virtual machine code. So you can consider this LLMV as a bytecode in some sense. That would be run on ARM machine, some sort of virtual machine code. And actually, the Ada, C#, Common Lisp, Crystal, D, Delphi, Fortran, OpenGL, shading language, Holiday, Haskell, Java, bytecode, Julian, Lua, Object-C, Poly, Python, R, Ruby, Rust, CUDA, Scala, and Swift. All of these will be translated to low-level virtual machine code, and that's what I said. It actually will be similar to this low-level code virtual machine bytecode. That will be the old-time C-level code, or similar to the assembly code, but depending on the implementation on your processor. So that is the low-level virtual machine. And here are the procedure for low-level virtual machine on ARM. So these are described in the textbook. So I read it through, but if you need to know, you have to find out the low-level virtual machine to understand what these are talking about. But these are in the textbook. So I start to read it. Saves into the local variable and the temporary area any caller save the register. So caller save register, caller right here is like here. Whose value still needed? Put up to 4 small arguments into register R0 and R3. What this is talking about, small parameter, is actually this argument, but the number is different, okay? That's the low level, but it's actually putting 4 small parameter right here. But these are 2 different machines, but it looks similar, okay? So that's the ARM's low level virtual machine. So put those small arguments there. Put the rest of the argument into the argument BO area at the top of current frame. So the bigger arguments, so they may be in the temporary or something. And then that's B1, B1S, which put return address to the register link register. So put the link register. Link register could be something like this, or could be something like this, different from the same register. It can be together or different. And you can put a friend address as well. So it depends on the implementation. But for this ARM sequence is something like this. And the jump to the target address. So actually you have the context switch right here. And then change instruction set coding. And in Prologue, code push necessary register onto stack. So put those save register by the code. Initialize frame pointer by adding a small constant to the SP pressing result in R7. Subtract the SP to make space for local variable temporaries and the argument BO area at the top of the stack. Epilog, the code put the return value into R3 to R0 to R3 or memory as appropriate. Subtract small constant from R7, putting result in SP. Pub save the register from stack. PC take place of the link register from Prologue. So these are different procedures that Coley will do if you are using the LLMV on ARM machine. After the call, the caller moves the return value to wherever it's needed. Restore caller save register basically over time as their value are needed. All arguments have space in the stack, whether passed to the register or not. The subroutine just begins with some of the arguments already cached in register and the tailed value in memory. Stale value in the memory means something that if it is out of date, we need to write through it. So actually, when we have the context switch or we after the call, we need to update and write through to the memory to make sure that memory coherence is maintained. So these are the low-level calling sequence for LLMV on ARM, but this actually just provide an example for the calling sequence. And this is normal state of affair. Optimizing compiler keeps things in register, whenever possible, flushing into memory only when they are out of register, or when call may attempt to access data through a pointer from the inner scope. So what this actually say is on our machine, let's try to optimize the use of the register window instead of making the real memory access for the call frames. So that's the idea for register windows. And that's what this say. And many part of the calling sequence, prologue or epilog, can be omitted. So sometimes you even not executing the calling sequence, particularly for leaf routine. What is leaf routine? Leaf routine is some function that don't call other routines. So in that case, you just store in the register. You don't actually execute the calling sequence, prologue or epilog to save those things onto memory, something like that. It's a waste of time. And then leaving the scene out save times. So leave scenes out. And simple leaf routine does not use the stack, do not even use memory, and are exceptionally fast. So basically, a leaf procedure is just call, extend the register file, and then after that you pop out the value in the register file, and you return to the process one, and you don't need to access any memory. So that's the leaf node for optimization. So this example in ARM actually show you some trick on saving the space or time for prologue over epilog. So basically, the call frame conceptually is always access the memory, but in reality, you are dealing with some register like this. And actually, it is actually put into the register file or register windows on this machine, something like this, instead of accessing everything in the memory. And by doing this, register windows will save your time. And this part, actually, I'm not following the textbook. So for those things, you need to study these different nodes. And these 4 lectures are very important, and actually is a little bit very confusing. So you need to be very careful and follow very closely. Otherwise, you will have some trouble to understand what is going on, because this parameter passing is a very, very abstract things and can be very misleading. And actually, for some people, for some reason, doesn't like C language, C++ language, because of their complexity on parameter passing. And for some language like functional programming, they all call by reference. So it will be much easier to do. So now let's look at this Java case. For Java function, we have a function or member function called setText. And we have a parameter list that is string type for text. This we call it as formal parameter. Formal means that's not the actual one. That is the definition or defined parameter. That is a string of defined parameter. And we have an object called label my name that set text. So a certain label in a certain GUI or something, we try to set it as Theosaurus, okay, whatever name it is. And this we call it as actual parameter. And remember, this actual parameter is what? It is actually a string. And in fact, it is a interned string. So interned string will be stored in the constant pool, not in the heap. So remember that this will be in the constant pool, not in the heap. So something in the constant pool, whenever you assign the same interned string to some other string reference, they will be accessing to the same copy. They won't access to a different copy in the heap. So these are actually the storage will be in the constant pool. And we call this as an actual parameter. But this actual parameter will be stored in constant pool, and the reference will be sent to here. So right here, actually, you will receive some sort of reference in Java language. So reference will be passed. And actually in Java, for some sense, this reference data type will be passing the reference instead of the and actually the reference itself is a value. So Java all support call by value, but they allow the reference to be passed. So actually Java in some sense have a mixed call by value and call by reference. And this call by reference or call by value actually is the parameter mode. So in this 4 lectures, we are talking about parameter passing, and in this first lecture, the lecture 3, we will be on the parameter mode, and we will start with the pass by value and 3 other different passing mode. And right here, you see a passing of the value, but the value itself is a reference. That's what Java achieved. So right here, we talk about parameter passing. Parameter passing mechanism have 4 basic implementation, or we call it parameter mode. What different mode actually we are passing? So you have the call by value, you basic pass the value in, and you have the call by value result by copying. You have reference by aliasing, and you have a call by closure or call by name. Many languages, including Ada, C++, and Swift, provides value and the reference directly. So you can actually have more than one mode of the parameter passing in a specific language. So right here, let's compare the parameter passing for pass by value and pass by reference. First, let's look at the C language or C++ language, and especially C language. C language only allow pass by value. And parameter pass by reference can be simulated with pointers. So this is not real pass by reference. It's actually a pass by pointers and pointers value. So right here, we declare a procedure that has 2 parameters. The first parameter is a x variable, and x variable's body is integer type. So x variable itself is a pointer. and y variable is an integer. So x body equals x body plus y. So x is a pointer. So whatever x referencing will plus with y and assign to x. So right here, we pass the ages of a variable, and a must be an integer. So the ages of a is passed to x, and x body, that will be a. So a will plus with b, and b is the y. The b's value will pass to y. So y got b's value, and x got the x actually pointing to the memory location of a. So it will retrieve the x value and put to here for the body of x. So these two are different. This one is actually passed by reference. The y is passed by value. So b's value passed here. So whatever y got updated, b will not be updated. But this is x is getting the ages of a. So body of x is pointing to the a. So whatever update like here will update to a. That's passed by reference. Or you can directly pass by reference in C++ case. And actually, right here we have call by reference. So right here it is call by value, and the call by value and the value is assigned to pointer to mimic the call by reference. And in C++, you have the call by reference mode. And this call by reference mode is actually makes C++ not as strong type. So right here, this x has this ampersand, and the ampersand sign or S sign that I call actually is a. And a for me, I would say ages before. For example, I always call this ages of a passed to x variable. But right here, you cannot read it as ages. You should read it as alias. So alias x is an alias of a. So remember, this call by reference in C++, the ampersand the sign or S sign is not a ages. You should call it as alias. So an integer alias x, that is an alias of a, and y is got a value of b. So y's value plus with the alias of x, that is a. So a's value passed to here, and then sum together, you assign to the alias x, that's for a. So you actually update into a. So this one, don't read it as ages or at. Don't read it as something like that. But this one is ages. So I call it at S sign at a. I pass the ages to this parameter that is actually the pointer. The body of x is updated with the body of x plus b's value, that is y. So remember this here, these two ampersand sign, this is no longer a S sign. This I call it S sign for ages. This please call it as alias. And alias is using this ampersand sign. So that's make it clear right here. These two signs are the same. This ampersand sign is overloaded. And before I read it as S sign, right now you should read it as alias. So alias x got the value. Alias x is an alias of a variable. And a will be changed after prefixal call, and this is direct passed by reference in C++, but not in C language. This is not valid for C language. Value and reference parameter, and if y is passed to foo by value, then the assignment inside foo has no visible effect. Y is private to the subroutine, and the program print to. So whatever parameter Y written down in here by passed by value, Y itself can be updated, and Y should be considered as a local variable. It has all the feature that a local variable has. Because what? Because the parameter is stored in here, and if you update it, it's in here, but it will not be read by the previous call frame. So local variable here and parameter right here, they are of the same operations in the new call frame, in the new function. And this parameter may be passed by previous function, but after that, it is exactly the same with the local variable that you see in current call frame or current subroutine. So right here, we are back to here. So call by value, we pass the 2 to x, and x have the 2 value assigned to y. So this is a local variable. Now you assign with 2, and then you update it with 3, and x has no change. So you still access the global variable x, that is 2. So this one is passed by value. Passed by reference is different. Y is passed to foo by reference, then the assignment inside foo function change x, y, this together because it's an alias, is just a local variable for x, and the program prints the 3 twice. So let's look at this. So right here, we call by reference, x is passed, but not passing the value, the right-hand side value to, it passes the left-hand side reference value of x. And then x, y got 2 because x reference is passed to y. So x, y share the same edges. And then y updated, x also got updated. So x got changed. So you will print x for 3 and x here for 3 again, twice. So in C language, we use this pointer and the edges of at v1, these 2 edges and the pointer to mimic the call by reference. But C++, I show you, it used the alias. And parameter passing, you have the input parameter and output parameter return value. This is for ADA. ADA control the parameter by semantics. Who can do what? So right here we have 3 types. One is in-type parameter. The callee only read. So actually this is similar to passing a constant to a certain function. Out variable, callee write and then can read. What does this mean? Actually, this means actually something like you actually will write a certain local variable and then return it. So this is more like a return value for output parameter. And in out actually is you actually read the data in and write it and actually modified. So actually this one is combined of a input and output parameter. So to understand the ADA's parameter, you better use this third, input and output. Not thinking about a pass by value or pass by reference. So input means you can read it, you cannot change it. Output, you can write it, and then you can return to the caller. And in and out, you can read and write. So ADA's in and write always implement is value result for scalar. So value in and result out for in and out. And for reference, for the structure object, it also is in and out. So this one is the value result copying we talk about here. It's a different mode that you had in for value, out for result. So it's like parameter and the return value. So return value, you can always view it as an outgoing parameter. Okay, next one. The next one, in a language with reference model of variable, ML Ruby pass by sharing. Okay, this pass by sharing is again different idea, and it's similar to pass by reference in obvious approach. It is also the option in function. If you pass a constant, the compiler create a temporary location to hold it. If you modify the temporary, who cares? It is okay. Call by reference and call by sharing, they are the same in the sense both they can change the value of the parameter variable. They are different in the parameter in call by reference. So actually, the call by reference pointing to another object, change the reference. So if it is a value, then call by is a simple value. And actually call by sharing and call by reference is the same. You just update the primitive data type. But if it is a call by reference to another object, change the reference, call by sharing cannot do that. So this actually is about what? About if you want to change the object, call by sharing is not allowed, and call by reference is okay. But if you don't change the object, you just change the value of that object, it is allowed by call by sharing and call by reference. So that's the difference between call by sharing and call by reference. And right here we have the read-only parameter. Read-only parameter in C, actually we have a pointer that actually pointing to this address of my record. So this is called by reference using pointer. So the parameter receive value from the caller, and the caller, the parameter variable will like a local variable. If it is called by value, and this is a call by value, and it is actually used for call by reference, but you cannot change this value because it's a constant. So you cannot change the object that it's pointing to. So in some sense, this one is to implement the call by sharing in C language or C++ language. If you do such a constant pointer type. Part 2 of the parameter passing, call by reference, call by name, call by closure. Now we move on to call by reference. And in fact, this lecture is more than call by reference. So right here, say in C++ language, we have an integer I, and then we create a alias j that's equal to I. So both of them pointing to I location. I equals 2, j equals 3. So I got affected by j because j is an alias. So read this as alias j, not address j. Not address j got updated by something. So this h sign, I repeat again, it is a overloaded as alias. This sign actually is ampersand sign, actually is a cursive for a later. So programmers who switch to C after some experience with Pascal modular Ada are often frustrated by C's lack of reference parameter. But C actually can modify by passing address then the formal parameter is a pointer, and then you need to explicitly reference it whenever it is used. C++ address this problem by introducing the explicit notion of reference, and thus call it as alias. And reference parameters are specified by preceding their name with the ampersand in the header of the function. So this one, I call it as alias A, alias A and alias B, and alias A and alias B actually, you actually use the T to hold a value, for A. So A's value passed to T, and B's value passed to A, and T's value passed to B. So this is a swap. But after the swap, A, B got changed. But not only A, B got changed, but whoever have the alias with A and B will be changed. This is called by reference, and this is used for swapping. It's quite effective, and actually it is in the sign of ampersand, but ampersand got overloaded. So for C++ language is different from C language. So right here I have a pointer. E is a pointer to an element data type, and we have this Ruby whatever chemical array element. We pass the address to here, so E is pointing to this record, and that is the element type. We talked about this element type before. So E's name, we use this goto sign. E pointer going to the data field name is aluminum, and go to the atomic number, that's 13. The atomic weight is 26.98 something, and the metallic is Chou. And this is the C language way of assigning the content for this element aluminum. But in C++, we can use the reference E that is referencing to this structure or record, and E.name equals aluminum, E.atomic number equals 13, E.atomic weight equals 26.98, E.metallic equals 2. So this ampersand sign E, this E actually is similar to Java's reference. So actually, this Java's reference, you just forget about this ampersand sign. This operation is exactly the same with Java's operation. And think about that. This is the reference type. And actually, I told you before, the Java language can use that reference type to mimic the function for pointers, and Java's reference is a little bit more complicated than C++, but or more convenient in some sense. And right here we have the discussion for this C++ reference type, and two are equivalent. And the next one I will talk about is this overloading of the double arrow, left arrow sign, that is a operator, double arrow, and it's overloaded for C++ language. Originally, this double left angle bracket sign is for the shifting function, left shift function. So this here actually been overloaded to the function of inserting a string to string. Insert the sequence of characters that conform value of str to os. This function overload this operator shift to behave as described in this for C strings, but applied to string object. So two parameters. First parameter is the output string. Second parameter is the string object. Return value is output string. So what this really be used for? We overload this left shift and right shift operator, return the reference to its first argument, which in turn pass to subsequent left double angle bracket, double left angle bracket, and double right angle bracket. So right here, usually we print these 3 string to the console output. So this is the output string, cout, console output. And this console output is shown for this. So actually, we have this operator as a function call, and 2 parameters. The first parameter is this cout, second parameter is this a. So actually, we combine this string into the output string. And the output string and this string with this operator provide a output, and that output is another output string with a string in there. So what this actually means is right here we have combined this output string with the string, and then return as a reference type is an output reference type. So you can think about this is a modified this whole thing right here from cout to a. This is another output string after the operation. So this output string will combine with b with the operator double left angle sign, and then this become another output string, and we put c into there again. So we actually print out ABC. That's what it is. And without referencing the left double angle bracket and right double angle bracket, we have to return the pointer to their string. If we have no reference type in C++ language, then what will happen is we need to use this as a pointer, and then dereference to this pointer, and then that will return the pointer, and then dereference into this operation. And it will be similar to this. We create a pointer, and then we find its body and use that, and we find this value, and then use that as a pointer, and then find its body to find this. But this actually will be come this. So this is not really a good idea to match this. This makes things too complicated and won't be compatible. So that's why in C++ we need to have this reference data type, and that is denoted by the alias sign, or actually it's the ampersand symbol. So now let's introduce one even more advanced reference value. It's called the R value reference, or double alias sign. So double alias sign string that actually means the object or body. So right value is this value in turns a string object, and this str is called L value, and this string is a object or body of string that is called right value. Okay, and R value denote for the temporary object. Temporary object is object, it's not reference. It's talking about object which don't have a name. Okay, let's look at an example. For L value, we have I, that's integer 42, that's okay. It updated to 43, that's also okay. And then we find the I's address passed to a pointer P. I is a L value, is a reference, so it's okay. The address of it, you can find it and pass it to it, okay. And then we define a full value of full parenthesis. That is a reference. It's a left-hand side reference, so it should be put on the left-hand side. And this left-hand side got assigned with 42. That's L value. That's okay. So you just treat this as a alias of something, of some integer. So it's an integer itself. Assigned by this value is okay. But to find this address of that this reference is okay. You find a pointer and assign to a pointer, that's okay. You find a address, assign it to pointer, that's okay. So this right-hand side part of this ampersand, you need to read as HS here, HS here. This one need to read as alias. My way of calling this different symbol will help you to understand it much faster. So right value, we have a full bar. This actually is a right value. This one is different from this definition that define left value. So because this is a function, you will return the integer. So this is an integer that is a right value. This one is the alias, that is a reference, and this is the left value. So we have a j equals 0, and we assign this function's result to j. This is return the value that's the right value to j, that's okay. But you find the address for a right value, you find the address of a right value, that's object itself, it's not a reference, it's not allowed. So this cannot pass. So right here, star A means pointer, alias A means reference, double alias A means the object or body that the reference pointing to. This is very important. So R value reference, first let's look at the copy constructor. Create or copy reference. R value reference allow an argument that would normally be considered as R value to be passed to a function by reference. So right here, we actually declare a object reference O2 equals O1. This is different from Java. Java will be passing the reference to this, but this in C++ actually means new object with the object 1, and then create a new object to O2. So these two actually have different copy. We call it the copy reference. And if you want to share the reference, you should create alias, not using this. This is copy constructor. Computer will initialize O2 by calling the object's copy constructor method, passing O1 as argument. The parameter of object's copy constructor will be constant reference, that is. The body of the constructor will inspect and decide how to initialize O2. If the state is mutable, the constructor will generally need to allocate and initialize a copy. This is not for string in Java. So basically right here, we create a new object and return the temporary reference T to this O3. That's a right value reference. Now let's look at the right value reference, alias A and double alias A. First, let's look at this double alias A, finding the object, double ampersand, no constant. So right here, we pass a object other in here. It's not reference. So this object's payload field assigned to payload. And this payload, other.payload got null. So this object actually been thrown away as garbage. But payload actually get the object. So this right-hand side value, this left-hand side value actually got abandoned, but the object is passed to payload already. So actually, the original pointer disappear. New pointer, you actually got it. This is called the move constructor. So actually, this payload will belong to the object. So actually, it's a data field got updated by a data field of another object, and that object got nullified, and the original object's payload get a value. A move constructor of class T is non-template constructor whose first parameter is T double alias, and the constant T double alias volatile T double alias, and the constant volatile T double alias. So there are several ways of doing this, and either they are no other parameters or the rest of the parameter all have default value. R value reference, alias A and double alias A, move constructor. Let's look at how things can be moved. So first, we actually try to move A. Okay. Second one, we actually use constructor to construct a object that actually return an object type. You pass a object in here, and this object A actually in F function is calling this A constructor, and it will construct a test string using this constructor. So the object being passed, the reference being passed to this A1 is a string reference, and this string reference put into the move constructor, and then assign it to A2. So this actually this A1 the string object, not a reference, will be moved, and then create a new string to pass back to the A2. So A2 refer to an object by moving away of the string in A1 object to the A2 object. This is called the move constructor. So be short, the move function, the move constructor, if you call this and then construct a new object, actually the effect will be you actually delete the original reference and then create a new reference to this A2 reference. That's the idea of you moving one object to the other object. The original one gave out a data object, and the new one got a copy. Programmer may know that a value will never be used after passing it as parameter, but compiler may not know. Programmer can wrap the value in a code to move function, and move generate no code. It is in fact a cast, and behavior undefined in the function actually contain the subsequent use of O3. So right here, you will move the object of the O3 to O4. But what happened to O3, we don't know, because there is no tail. So basically, using to call this F function, actually this A will be calling this A constructor. You will create a test object string and pass to this A, and then that have a temporary object holding this test string will pass to A1, and A1 will reference to this test object as a string. This test object as a string, and then you create a A2 reference to this test as well, and then you remove the A1 reference. Call by closure. What is a closure? A closure is a reference to a subroutine together with its reference environment. And it's different from C's macro. C's macro is just copy the whole code into the C program. Alias closure is different. Closure is actually passing the function. So right here, we have a function definition over here. It takes two parameters. One is an access function. The other one is an array of integer. And the definition of the function over here. And this is called apply to A function. And apply to A function actually pass the function add k to the access function. So actually this is the assignment. And actually this is calling this add k. And also you pass the parameter b, that is a array, passed to this apply to A right here. So basically this f function would be the add k function, and you pass the actually the A array in here. So actually this one is actually would apply this add k to this b function. Other call by closure in C, C++, it's easy to understand. You have to use pointer. So in the declaration of the f function, you should use f as a pointer, and the f pointer can be used as the function call name. That is how you pass a closure. Basically, you just assign the address a function to here, and the function name actually is an address to a function, and it will be treated as a pointer. And they pass in here, matching there, you will be able to run this f function on the A and A size for A array. And in functional language, you don't need to use that pointer reference type, a lot of symbol. You don't need that, because in functional language, you actually pass by reference for those functions. So actually, you just put a name over there, and it will finish it for you. So subroutines are routinely passed as parameter in functional language, so it's no special thing that you need to do. And a list-based version of apply to A would look something like in the scheme. So call by name is the old term for OGO technique. Think of it as call by textual substitution. So basically, you have the call by name, you just copy the function over, just like a macro. And call by name is used in OGO 60 and similar, and call by name by Miranda, Haskell, and R language. So right here, the figure 9.3 is a summary for the parameter passing mode. And you can read it. And let me know if you have any question. Now we are going to touch the parameter passing part 3, special parameters. Let's look at what are the special purpose parameter. There are 4 kinds: conformant arrays, default parameters, name parameters, and the variable number of arguments. The first one is conformant arrays. Conformant array is easy to understand. A formal array parameter whose shape is finalized at the runtime, not the compile time. So sometimes we have in C language, we have integer bracket A as an array, but that array you don't know about the size, and it is not defined. And it may define in your function somewhere you actually assign it with an array of 5 elements or something. So that size is not determined. We call it as a conformant array. So that actually need to be defined. The shape needs to be defined at runtime. We call it conformant array. So here is one example. And default optional parameter, actually right here for Ada, we have a field that is an integer, and from range 0 to integer's last value, and number base, it will be ranging from 2 to 16 for different base. And default width field using the integer's number width, that is the field size. And the default base, we use 10 base. And if you, in functional call of this part, put procedure in Ada, if you don't put any parameter, actually you would use the default value. For example, for the number base, you will use 10 base. If you do not assign any parameter there, we call this as default parameter or optional parameters. One common use of default parameter is in I/O library routine. For example, default with print to console, and that is the default parameter for I/O device. The declaration of the default length use the built-in type attribute width to determine the maximum number of columns required to print an integer in decimal on the current machine. So this one is actually, for example, we have a integer we know that is 10 digit, and this field will reserve 10 digit for this in parameter field. Any formal parameter that is assigned to a value in its subroutine heading is optional in Ada. In our text IO example, the programmer can call put with 1, 2, or 3 arguments. So 2 have the default value, and at least you need to assign 1, and at most you can assign 3. No matter how many are provided in a particular call, the call for put can always assume it has all 3 parameters, and for those missing one, you will use the default value. The implementation is straightforward. In any call in which actual parameters are missing, the compiler pretends as if the default has been provided. It generates a calling sequence that loads those defaults into registers and or puts them onto stack as appropriate. Third one, we talk about the name parameter, and this name parameter, in combined with the optional or default parameter, will be creating the variable number of arguments and the name parameters. So that is 2 different techniques that can be used for different way. So in name parameters, basically, you not just put in the parameter there, but you also put a name there, and you can do it in position. So passing 33 to item, passing 8 as a base to the items. And actually, you can do it out of order. You assign A to base, put it on the position that is usually put in the item, and assign 37 to item. Or you can mix. Use the 37 in position and the base out of position. Of course, this is only one parameter, and you don't see it. But sometimes if you assign a format for HTML page, you have so many parameters, and you can do it all out of position, and some are missing. So you have the out of position assignment for the arguments, and you also can have a variable length of the arguments. In all our discussion so far, we have been assuming that parameters are positional. The first actual parameter corresponding to the first formal parameter, the second actual to the second formal, and so on. In some language, including Ada, Common Lisp, Fortnite, Modulus 3, and Python, actually Python support the the default parameters, and also permit the out of order assignments. Parameter passing part 4, return value. And return value, as I mentioned, it can be an outgoing parameter. So functional return, there are several ways. The first, more common way is the return statement. And return value is an outgoing parameter. So return the result of an expression. So you can put an expression here and use a return statement to return it to the caller. And you can put a value of a variable. So you actually updating this variable quite often. And at the end, you return this the value of this variable. And it's the second way of using the return statement. The last one, you don't put anything, then this return will be considered the break of a function. The syntax by which a function indicates the value to be returned vary greatly depending on the language. In August 64 Chain Pascal, a function specifies its return value by executing an assignment statement whose left-hand side is the name of the function. So basically, these need to use the name for receiving of the variable functions. A function that has figured out what to return and does not want to return, yet can always assign a return value to a temporary variable. In this case, it is this RTN, and then return it later. Function return, incremental computation of a return value. This one is very apparent. And you actually define a RTN, that's an integer, and you keep computing on it until you return RTN. So this is incremental computation of a return value. Here, RTN must be declared as a variable so that the function can read it as well as write it. Because RTN is a local variable, most compiler will allocate it within the stack frame of A max. And I say this is easy. And usually you will see such incremental computation of a return value, such as a sum of a certain array. You keep updating the sum, and then you return it. Those are the incremental. At least that is a good example for incremental computation of a return value. The return statement must then perform an unnecessary copy to move the variable's value into the return location allocated by the caller. Function return, explicitly named return value in SR. In SR language, you can use a outgoing parameter name with return assignment over here, that's RTN. So some language eliminate the need for a local variable by allowing the result of a function to have a name on its own right. Here, RTN can reside throughout its lifetime in the return location allocated by the caller. A similar facility can be found in LFL, in which every function contains an implicitly declared object named result. This object can be both read and written, and is returned to the callee. Returned to the caller when the function returns. And some function can return multiple values, especially like Python. You can return 2 values at a time. ML and its descendant and the several scripting language allow multi-value return function to return a tuple of values. Many languages place restriction on the type of object that can be returned from function. In Audacity and Fortune 77, a function must return a scalar value. So for some language, you cannot do this parallel value. In Pascal, an early version of Modular 2, it must return a scalar as pointer. In imperative language are more flexible, and many implementation of Pascal allow function to return value of composite type. Okay, we will finish our session today up to here, and we will resume on Thursday for session 2, starting from the exception handling. Thank you. Bye-bye.